is lesson 4.2, graphing linear equations. You should be on page 215. An example of an equation in two variables would be, like here, 2x plus 5y equals 8. A solution of an equation in two variables, and this should be something you get in your notes, is an ordered pair xy that produces a true statement when the values of x and y are substituted into the equation. Here would be an example of a solution to this equation. If I made x 1.5 and I made y 1, so if I had the ordered pair 1.5, 1, if I put a 1.5 in for x, 2 times 1.5 is 3, and if I put a 1 in for y, 5 times 1 is 5, do you see how that's producing a true statement of 8? So 1.5, 1 would be a solution to this equation in two variables because 1.5, 1 makes this a true statement. There would be other solutions to that. This would just be one of them. Okay? Let's try another one of that here. We want to tell if this is a solution of this equation. Well, let's try. I'd have to put a 4 in for x because this is my x value, and I'd have to put in -0.5 in for y because that's my y value. Let's try that. If I put a 4 in here for x plus 2 times -0.5, am I going to get 5? That's the question. Is this going to equal 5? Let's try. I got 4 here. 2 times -0.5 is -1. Does that give me 5? And the answer is no, that's not equal to 5. So no, this is not a solution to that equation. So that's one thing you're going to have to do in the bookwork, and that's one of the I cans for this lesson, that you can tell whether an ordered pair is a solution or not. It's easy. Just plug it in and find out. Graphs. The graph of an equation in two variables is the set of points in a coordinate plane that represent all solutions of the equation. Now that sounds kind of complicated. It's not. This is saying that when you have an equation in two variables, you're going to have more than one correct answer. Because there's so many correct answers, we normally draw a picture of it with a graph. Here would be an example of that. X plus y equals 5. Let me make a little table. You know, if I put a 1 in for x and a 4 in for y, wouldn't that make the statement true? 1 plus 4 does equal 5. But what if I put a 2 in for x and a 3 for y? Well, that works also. What about 3 for x and 2 for y? Well, that works also. What if I do -10 for x and 15 for y? Well, that adds up to 5 also. There are infinitely many correct answers to this equation. That's why we end up graphing it. If the variables in an equation represent real numbers, one way to graph the equation is to make a table, which I just did, and then plot enough points to recognize a pattern, and then connect the points. So that's one of the things we're going to do today. You'll notice here, they say graph an equation. So that's one of the things we'll be asked to do is graph these. Let's try on this problem right here. So here was the problem, -2x plus y equals -3. They want us to graph it. Here's the first thing I'm going to tell you to do. Let's get in the habit right now of, starting today, writing these equations so that y is a function of x. In other words, remember, that means get y by itself. So to get y by itself, we're going to add 2x to each side, and we'd have y equals 2x minus 3. Now, if you write it in this form, it's going to be very easy to make a table. Let's make a table and find the pattern. So to make a table, I could either use my calculator, I'll show you that in a minute, or I could do it off the top of my head. I'm going to do it off the top of my head, and you follow along. I'm going to plug in 0 for x first, and let's figure out what we get. 2 times 0 is 0, and 0 minus 3 is -3. There's 1 point. Let me graph it. 0, -3 is down here. My next point, let's plug in a 1. 2 times 1 is 2. 2 minus 3 is -1. Okay, let me graph that point. One right, one down. Let's do another point. Let's plug in 2. 2 times 2 is 4. 4 minus 3 is 1. 2 right, 1 up. Let me get one other point. Let's do 3. 2 times 3 is 6. 6 minus 3 is 3. 3 right, 3 up. I'm starting to notice a pattern. This looks like a straight line through these points, so let me take my ruler out. I'm going to draw a straight line through these points. We do that here. And then I'm going to quickly check, is this line correct? If this line's correct, I ought to be able to pick any point on this line and plug it in here and make it true. Okay, here's a point right here. 5, 7. Let's see if that works. X5, Y7. If I plug in a 5 here, does this work out to 7? 2 times 5 is 10. 10 minus 3 is 7. You notice any point on this line will make this statement true. Now, here's why I told you to write the problem in the beginning. You might be wondering, well, Mr. Lemansky, I could have got these points without doing what you told me to do here. Here's why I want you to do that. If you write it in this way, you can use your calculator. And this is so cool. Instead of having to do it in your head, let's take our calculator and do it. So y equals 2x minus 3. Let's type that in our calculator. So I'm going to hit the y equals key right here. I'll type in 2. This key here stands for variable, so 2x minus 3. Okay, do you see above the graph key where it says table? If I hit second table, my calculator will make a table of all those points. Now remember how we just got done figuring out that when you plug in 1 you got -1 and you plug in 2 you got 1? Let me go back and show you that slide real quick. Oops, there we go, right here. Can you see 1, -1, 2, 1, 3, 3? When I go back to my calculator, you're seeing those same points. My calculator could have done this for me. So you can do these in your head if you want, but your calculator can assist you. That's why you always want to write these so that y is a function of x. Anyway, there's my equation. There's my graph. So I've now answered the question. It said graph the equation. I just did. It's right here. Make sure we draw a line through those points. Put arrows at the end. The arrows at the end signify that this is going on forever. A linear equation is an equation whose graph is a line. Let's get linear equation in our notes. Make that note. It's an equation whose graph is a line. I'm going to underline. Do you notice in the word linear, you see the word line? So linear equation means straight line graph. So any equations that are linear will be a straight line graph. Now linear equations come in 3 forms. One form is called standard form, and you see an example of standard form. I'm going to highlight it right now in green. It's right here. An equation that looks like this is in standard form. So if you look at the previous problem that we worked on, let me go back one slide and look at that previous problem. Do you notice how this problem right here started off in standard form? Okay? Let me write it up on top in blue. AX plus BY equals C. Just like this says in the book. AX plus BY equals C. Here's my standard form. A must have been -2, B was a 1, and C was a -3. This equation was in standard form. It's not always easy to graph in standard form. That's why I rewrote it into this form. Okay? Now, the second form of linear equations is called slope-intercept form. You will learn about this form in the upcoming days. We're not going to talk about it more right now, but we will learn this form thoroughly in this chapter. And there is a third form we're going to work on at some point here in the next several weeks, point-slope form. All of these forms are linear. So anytime you see it, as soon as I see an equation in this form, I immediately am thinking in my head, aha, that's a straight line graph. Okay? because it's a linear equation. Standard form will always be linear. All right, next. Let's talk about two special circumstances that come up, equations of horizontal and vertical lines. A horizontal line means one going straight across your paper. Horizontal lines always have this form. It's always going to be in the form, and you see it here in this little key concept box. It's always going to be in the form y equals b, or y equals whatever number it's passing above, okay? Or passing through, I should say. Let me give you an example of that. It's up here. I circled. Let's look at this, okay? This will make it clear why horizontal lines have an equation y equals b. They wanted me to graph, and I'll highlight it here, they wanted me to graph y equals 2. So let's think about y equals 2. I'm going to make a little table. Y equals 2 means that y is always a 2. It doesn't matter what x value I plug in. If I plug in negative 2 for x, I'd get y as 2. If I plugged in 0 for x, I'd get y as 2. If I plugged in 3 for x, I'd get y as 2. So let's plot those points. Negative 2, 2 is here. 0, 2 is here. And 3, 2 would be 3 right 2 up. Do you notice how this line, can you see how the y values are always a 2? That's why a horizontal line, in this case, would have the equation y equals 2. Okay? If I had a line, let me put another line on here. If I had a line up here 5 units above the origin, that line would be called y equals 5, because every point on that line, it has a y value of 5. Okay, here's another special circumstance. Vertical lines. Vertical lines have the form x equals whatever number that horizontal line is passing through on the x-axis. Okay, let's take a look at why that's the case. Okay, so here we have x equals negative 1. Let me highlight that. So we're going to graph that. X equals negative 1. Let me make a table of x equals negative 1. Okay, that means x equals negative 1 means x is always a negative 1 no matter what y is. Okay, if x negative 1, y could be a 2. If x is negative 1, y could be 0. Y can be anything. X always has to be negative 1. Let's graph these, and you can see it here. Negative 1, 2 is 1 left, 2 up. That's here. Negative 1, 0 is 1 left, 0 up. And negative 1, 1 is 1 left, 1 down. Do you notice how it's creating this vertical line? X equals negative 1 is a vertical line through the point where x is negative 1. Okay? So these are two special situations you want to be aware of, because in the homework they will have you graph some horizontal and vertical lines. Okay? Let's try a few here. It says graph the equation y plus 3x equals negative 2. Okay, so step 1, let's solve for y. I'll take away 3x. And I have y equals negative 3x minus the 2. Just to save some time, I'm going to put that in my calculator. Let me clear the last equation. So y equals negative 3x, negative 3x I meant to say, minus the 2. Okay, let me make a table. Second table. There's my table. There's a whole bunch of points. I got more than I need. Okay, let me graph these. I have 0, negative 2. So here's 0, negative 2. I see 1, negative 5. So here's 1 right, 5 down. I see 2, negative 8. So I'm going to graph 2, negative 8. And since this problem, can you see how this problem is in standard form? This is, I'll put SF for standard form. If it's in standard form, that means that this is a linear equation, which means it's a straight line graph. Can you see the straight line developing? All I got to do is take my ruler now, and I want to draw a straight line through these points. So I'm going to do that right here. And don't forget, when you're done, put an arrow at the end, because any point on this line would make this statement true. Okay? So, for example, I see the point negative 1, 1. If I plug in a negative 1 for x and a positive 1 for y, this is going to work out to negative 2. Let's also graph y equals 2.5. That's one of these special situations here. So y equals 2.5 means, go to your graph paper, and I want to graph y equals 2.5, so I'm going to do that. So let's go 2.5 units up. That's where y is 2.5. And all of these y's are, see, I'm drawing a straight line here. I'm just going to draw a horizontal line at y equals 2.5. That's what that graph would be. There's a graph for y equals 2.5. Okay? Let's also graph x equals negative 4. That's one of these special situations. The horizontal line at x is negative 4. So I will go to negative 4, which is here, and I'm going to take my ruler out, and I'm going to draw a line vertically at x is negative 4. That's what this line would look like for that problem. So really, we don't even make a table for those. That's just, we have to know the horizontal and vertical lines have a special, that's a special case, I guess you could say. A little reminder here about a linear function. Remember early in chapter 1 we learned, or I should say at the end of chapter 1, we learned that a function means each input can only produce one output. Each input can only produce one output. That means this situation is not a function. Okay, the other situations we looked at are, but this one is not, because when you look at this situation of the vertical line, look at what my table would look like. See, if I plug negative 4 in here, it's producing 0 for y, but if I plug in a negative 4, I could also get a positive 1 for y. Is it making sense? Here's another one, negative 4, 2. This is not a function. One input is giving me different outputs. So vertical lines cannot, it's a linear equation, but it's not a linear function because functions, each input only give you one output. And then to end the video, I want to just walk through this real quick. Graph a linear function. It says graph the function, we'll do this sample here, y equals negative 3x plus 1 with a domain of x less than or equal to 0. Then identify the range. Okay, so there's my equation. If I want, I can make a table on my calculator. Let me go to my calculator and do that. Y equals, we said the problem was negative 3x plus 1, so negative 3x plus 1. Let's make a table. Second graph will give me a table. Now, we got to be careful here, because remember, the domain, the x values can only be less than or equal to 0. So my calculator doesn't understand that. My calculator doesn't think. It just produces results. So I have to understand that these results I can't even use, because do you notice the x values here are all bigger than 0. I can only graph the values that are less than or equal to 0. So I'm going to scroll up here a little bit, and here are some values for x that are less than or equal to 0. So I could plot 0, 1, negative 1, 4, and negative 2, 7. Let me do that right now. So I said 0, 1, negative 1, 4, negative 2, 7. So I plotted those points. Now it's apparent when I plot those that I'm getting a straight line, but remember, I can only graph the points with an x domain of x less than equals 0. So in other words, I kind of have an imaginary wall right here. I'm drawing a red line. I can't graph past here because this is where x equals 0. So my graph would look like this. It's not a line, it's just going to be a ray going in this one direction only. There would be a graph of all the values that are less than or equal to 0 for x. Now, one other thing they say, they want the range also. Okay, now remember, so my domain are all the values less than x. The range, remember, that means my y values. Remember on our table back in chapter 1, these were the domain values here. I'll put range for the r's. These values were the range. Well, let me see. What kind of points do I get from my range? Y could be 1, 2, 3. It keeps on going up. My range is all the y values that are greater than or equal to 1. Do you notice? This is the lowest I go on my graph. My lowest y value is 1. So my domain is x less than equals 0. My range is y greater than equal 1. I'm going to stop the video here. If you have questions, you can ask during class.